The heart of chemistry is about molecules rearranging bonds, that is, undergoing chemical reactions. When chemical reactions occur, we've said they obey the law of conservation of mass. That is, the number of atoms we start with must be equal to the same number of atoms we end with. What makes a chemical reaction different than something like a phase change is that bonds are broken or atoms are rearranged during the chemical reaction. When we write chemical reactions, we write our initial material or our reactants, followed by a reaction arrow pointing to the right, and then our products. If we need multiple molecules in order to balance the reaction, then we can put a number in front of each molecule to indicate that we need so many of that particular set of molecules in order to have a balanced chemical reaction. If you have a balanced chemical reaction, then when you count up all the elements on one side, you'll find you'll have the same number of elements on the other side. So the same atoms, or the same number of atoms, will appear on the reactant side as the product side. If this isn't the case, then you don't have a balanced chemical equation. Now, before going through learning how to balance chemical equations, I thought we'd talk about the different types of chemical reactions there are out there. So, we're going to study acid-base chemistry or neutralization reactions, combination reactions, combustion, decomposition, double replacement, redox, and single replacement reactions. We'll start off with a combination reaction. A combination reaction involves two or more molecules coming together to form one new type of molecule. Now, when I say one new type of molecule, don't confuse that as meaning one particular product. You can have multiple iterations of the same product. In the examples below, the first two chemical reactions are combination reactions, but you'll see in front of the product there's a 2 there. That's just part of the balancing. So combination reactions, there's only one product, but the coefficient in front of it can be any number. It'll always be an integer number, it'll always be positive, but you will always have one type of molecule when you're done with a combination reaction. Decomposition reactions are just the opposite. We start with one type of reactant, and we end with 2 or more molecules as products. So here's several instances of something breaking down: calcium carbonate, potassium chlorate, sodium azide. All are examples of decomposition reactions. Combustion reactions are probably the ones you're most familiar with because they involve the release of energy during the course of a reaction. All combustion reactions must have oxygen and an initial source of energy in order to be classified as a combustion reaction. We often burn carbon molecules, although those aren't the only things that can actually combust. We can burn metals, for example. So, most of the time in chemistry, what we're going to do when we talk about combustion reactions is just give you the initial reactants and expect you to figure out what the products are. Now, here's the thing. All combustion reactions produce carbon dioxide and water, both as gases. So anytime you see a combustion reaction and you don't have the products there, I'm telling you right now, it's going to be carbon dioxide and water, both in the gas phase. So, combustion reactions must always have oxygen, must always have an initial source of energy to get the reaction going. Single replacement reactions just involve one element replacing another in a reaction. So in the top reaction there, we have zinc metal plus copper chloride solution producing zinc chloride. So what's happened is the zincs come in and replace the copper, and the copper is just left and has formed solid copper. So metals will replace metals in single replacement reactions, and nonmetals will replace nonmetals in single replacement reactions. So be careful. Always replace a metal with a metal or a nonmetal with a nonmetal. In the second case, we've got liquid bromine reacting with potassium iodide to form potassium bromide, and solid I2. Now, with these reactions, we have to use what's known as an activity series to actually predict whether or not the reaction occurs. Because elements have different reactivities, what we've done is we've generated a series of reactive metals and where they fall in terms of their reactivity to each other. Now, you don't have to be able to memorize this, but you do need to be able to apply it when taking an exam. I'll provide you with the activity series if you need it for the exam. So what we see here is the most reactive metals at the top, so lithium, potassium, and barium, for example, and the least reactive metals at the bottom, mercury, platinum, and gold. And perhaps this makes sense to us when we think about everyday life. When we go out and buy jewelry, what's jewelry made out of? Well, gold, platinum, silver, copper, hopefully not mercury, but you can see those metals are all at the bottom of the activity series. They are really inactive. They don't want to react. In fact, it's hard to get them to react. And so as a result of that, we've made jewelry over the years, not because copper was shiny and pretty, although it's a metal. Could have made it out of zinc. The only reason we chose copper or platinum or gold was because that it's not reactive. So you would wash your hands and your ring doesn't dissolve. So when we apply these, this activity series to a reaction, what we do is we look to see where our metal falls with respect to the ion that it's trying to replace. So I'm going to go back a slide for a second, and here we see we've got zinc trying to replace copper. So the way we're going to figure this out is by finding zinc on our let's see here, on our activity series here. So we see zinc right there. Whoops. And we can see copper's down here. So zinc metal is higher up on the scale than copper. Therefore, it is more reactive and the reaction will take place. Let's try another one. Let's see if I can write on the screen here. We'll go with a pen. So let's try and see if gold would react with silver chloride. In this particular instance, we can see gold is down here. And because it's at the bottom of the activity series, it's not going to react with anything. Silver is above it. So if the ion falls above the metal, no reaction will occur. So we would just write no reaction, or NR. So that's how we can use the activity series to determine whether or not a single replacement reaction will occur. Let's talk about double replacement reactions now. Double replacement reactions involve two ionic compounds simply switching cations. As a result of this, cations end up with the anion of another compound. So again, in this case, we would have silver here wanting to pair up with chloride to produce silver chloride. Potassium will come over and react with nitrate to form potassium nitrate. Remember, be careful when you balance these to always write the metal first, or the cation first. Like single replacement reactions, double replacement reactions are something you're going to have to be able to predict what the product is. It's not something that you're going to be told. Now, when we do double replacement reactions, what we're looking for is a solid, liquid, or gas forming. If all our products remain aqueous, there is no reaction. So how can you tell if something is going to form a solid, liquid, or gas? Well, for the solids, we've got the solubility rules. The solubility rules tell us what forms a solid or what won't dissolve in solution when the cations and anions are brought together. So you can see here on the first case with nitrate, anything with an NO3 on it is going to be aqueous. Doesn't matter what the cation is. Something with an iodide ion in it is going to be aqueous as well, unless it's, for example, silver iodide, or lead 2 iodide, or mercury 1 iodide, in which case those would be solids. The insoluble compounds never dissolve into solution unless they're paired up with their exceptions here. So, for example, Na2S, sodium sulfide, would be aqueous because it contains a column 1 element from the periodic table. So that's also known as the alkali metal column. So those are the different types of reactions, and in the next unit we'll go through and learn how to balance chemical equations.